happy to welcome Professor Kuniba from the University of Tokyo, who will give 3 lectures. The first one is this morning, and the next 2 lectures will be next week. The first one is about multispecies ASEP and the t-PushTASEP in a strange 5-vertex model. And thank you very much, Maureen, for making this work.
Thank you so much. Good morning. And yeah, I thank the organizers for the invitation. I'm very happy to be here. So I'll talk about this topic. And so this talk, well, where should I start? Around here? So this talk is an elementary exposition of algebraic and combinatorial aspects of inhomogeneous t-PushTASEP and ASEP on 1D periodic lattice, which becomes intriguing in multi-species setting. So it's essential to have a multi-species situation. So here are some contents or keywords. So anti-symmetric fusion of strange 5-vertex model, Holstein Markov realization of UQ, and 3D interpretation of stationary probability, and so on. So my talk is based on 2 papers. The first one is the one with Masato Okado and Travis Screenshot last August. And the second one is more recent. It's a paper with Irvine IR, so posted rather recently. So let me recall what's inhomogeneous N-species t-PushTASEP on the link. Actually, there are several versions of this model studied by several authors in here, listed here. Maybe it's not a complete list. But in this talk, I particularly focus on the one studied by the Iyer, Martin, and Williams in 2024. So it's the system on 1D periodic chain with L sides, where each side I takes a value from 0 to n. And 0 means empty side, and 1 through the end means the color or species of the particles. So let's B denote the space of one particle states. It's an n plus 1 dimensional space. And the space of the states of the t-PushTASEP is a subspace of the L4 tensor product, specified by the multiplicity array, integer array, like this. That means Mi is a number of particle type I particles. So this ASEP dynamics preserves this data or multiplicity M. So it's acts on the subspace. And I assume that Mi is not 0. So it's always greater than 0 for all I, including 0 and n. And this I take from this paper, so this notation, Ki. So I would use this notation very frequently in my talk. So it's a continuous time Markov process governed by the master equation of this form, where the Hamiltonian or Markov matrix takes this form. So this notation I will also use in many places here. So this is a coefficient of the diagonal term, but so the essential part is a non-diagonal part here. So this factor is the transition rate from the state sigma to sigma prime. And it is defined rather non-trivial manner. So let me try to explain it. So this transition rate is 0 unless very specific condition is satisfied between sigma and sigma prime. So there must exist a strictly decreasing sequence of colors, A, B, C, and so on, D. And so what does it mean? So at some site J, let's call it site J, so largest color particle gets activated, and it moves to the right periodically and push out the smaller species particle P. So it sits here in sigma prime. And the kicked out particle P does a similar thing for the other, and sequentially like this, until the last smallest particle settles at some vacant site here. So if sigma has this form, then sigma prime has this form, and all the other dot part remains the same between sigma and sigma prime. So if this condition is not satisfied, this transition rate is 0. And if this condition is satisfied, then the transition rate is given by this formula, where 1 by xj is an inhomogeneity parameter attached to the lattice site j, continuous parameter. So there are L, and L is the system size, periodic. And for each arc, you have some factor. And how to determine this factor? It's given like this. So it's defined with respect to the initial state, sigma, not sigma prime. So you look at sigma state configurations. And for this arc, where this depends on what the target is, so it's given by this formula. So I already explained this notation here. And the T is an parameter of the model. And the definition by H is here. So namely, it counts the number of sites where there are strictly smaller color particles, including vacancy, between in the strict interval without boundary endpoints, in the sense of periodic condition. So this defines the dynamics due to this paper, so AMW paper. So it's quite complicated. And so even in one-time application of this Hamiltonian, it involves some sequential move of the many particles. So it's quite non-trivial dynamics. So for example, if it acts on the four-side chain like this, you get this result. For example, if you look at this factor, so the denominator x3 indicates that the process started from the third side, which is 2. So T2 just pushed out, kicked out this one, and this one went there like this, and so on. So this is an example. So our first theorem is the following. So this complicated Hamiltonian is expressed as an alternating sum of Tk, differential of Tk at 0, with some constant diagonal matrix L. So what is Tk? This is the main object in the right-hand side. So Tk is a commuting transfer matrix for the UTSLn plus 1 hat vertex model, where K runs from 0 to n plus 1. They are all commuting, not necessarily with respect to spectral parameter Z, but also K index. So Z is a spectral parameter, and Xj is the inhomogeneity at site J. So what's the meaning of this K index K? What does it specify? So it specifies that the auxiliary space of this commuting transfer matrix, probably you are familiar with construction of the commuting transfer matrix in the integral systems. It has got some associated auxiliary space rather than the space that it actually acts on. So auxiliary space is a K's fundamental representation of Vk, where V1 is identified with the space of local state P, n plus 1 dimensional space, or degree K antisymmetric tensor representation. So if you hear about the antisymmetric representation, you may feel that there will be a lot of sign factors in many places. And how can it be that something related to the probability? How can it fit the probability interpretation? So that intuition is indeed correct. So individual transfer matrix is not stochastic, even at 0 or differential. Stochastic, the definition of stochastic, for example, includes that the matrix element is non-negative, or that sort of things. But nevertheless, what this formula is doing is that it's a kind of inclusion-exclusion principle that selects sequentially particle transitions that I described, and while canceling all unwanted channels. So this alternating sum is a sort of inclusion-exclusion principle involving superposition of the commuting transfer matrix. So this is a kind of new feature. And also new feature is in almost all the literature in the integral probability, people deal with the symmetric fusion, but this time we deal with anti-symmetric fusion. So
that's a good Markov matrix. How do you prove that this is a good Markov?
Yeah, so that's a proof. Yeah. So that's a technical thing. And unfortunately, I won't have time to introduce, explain the proof, but.
Then I had another question. Yeah. Is there a good T equals to 1 limit
T goes one limit. Maybe that's a good question for Professor Williams.
Does it have to be younger?
Yes, probably it's okay. Yeah, because it's defined, element is defined by T analog of the T integer, and which is not singular. So yes, I think it's well defined. Yeah. Yeah.
Quant à symétrie de Youngien? Quant à algebra de Youngien, then?
Well, that I don't know, but yeah, that's a naive expectation. Yeah, because yeah, T deformed algebra at T equal 1, yeah, basically it should be something like that, yeah. So let me explain more about this, because this is a fundamental object of our result. So let me explain a bit more about this transfer matrix TK. So I said that the auxiliary space is indexed by K, and K, this is PK, so case anti-symmetric representation. So maybe to get familiarized with this representation, it's good to know the labeling set of its base. So there are two natural labeling sets of the base. One is a tableau representation. Another one is a multiplicity representation. So this representation space has a base labeled with the depth K column strict standard tableau. So these capital AKs, the alphabet, which are going to be inscribed in this column strict tableau of depth K. So these are the letters. So that's one set of the labeling of this representation. And another set is the so-called multiplicity representation. So this little AI means the number of the occurrence of the letter I in the tableau. So this little AI takes just 0 or 1. And there can be n plus 1 letters that you can use to fill the column strict tableau. So you can also label this, the base of this representation in this manner. So TK or PK. And now this transfer matrix defined by this formula, where this matrix element is pictorially drawn in this rather standard picture for the commuting transfer matrix. So here you have vertically the space of the local states, sigma 1 to sigma 1 prime. But what I said, the auxiliary space runs horizontally. And this K controls the thickness of this horizontal arrow. So depending on the K, depending on K, you have thicker and thicker vertical arrow. So for example, if K is 1, so I should draw just the same size, same thickness arrow horizontally. Anyway, so K is 1 case is also included. So you see that the building block of this transfer matrix is just this vertex, elementary vertex, and that's our matrix. And so in order to specify it, I need to specify the matrix element labeled by two pairs of this base label or column strict tableau, and also the two indices, sigma 1 and sigma 1 prime correspond to this space, so the 0 to n plus 1. So this is explicit matrix element, even here. So as I mentioned, certainly there are sign factors here. Very kind of annoying. And this is a special case of the quantum R matrix, which I do not like this, K1 and K2. So my convention is sorry. Yeah, so this is specifies the degree of the anti-symmetric tensors of which the R matrix is acting. So this corresponds to the special choice where K2 is 1 and the K1 is K. And so the basic case is both K1 and K2 is 1, and this is very well known, and given like this. And so this SK1 is obtained from the 3D L operator or anti-symmetric fusion of S11, basic case. So let me explain a bit about the anti-symmetric fusion. So if you have R matrix, then it has a singularity. By singularity, I mean that it becomes degenerate at some point. And there are two degeneracy for this R matrix. So Z equal T is a popular symmetric fusion point. But there is also another point where this becomes essentially anti-symmetrizer, which is Z, which occurs at Z equal T inverse. So the definition of matrix element is this. Practically formula is this. So this is a result of the fusion construction. So you compose this basic R matrix K times with appropriate spectral shift, reflecting this anti-symmetric fusion. And what's more, you need sign factors here in order to perform this anti-symmetric fusion. So this is a bit of calculation, but the end result is not particularly so messy, but it involves sign factor. So that's a way how this matrix element popped out. And as I mentioned, it's a building block of this construction. And the t-PushTASEP Hamiltonian is expressed in this manner. So that's our result. So let me give you one example. So this I already given you an example. Our formula is, so this t-PushTASEP is expressed as alternating sum of the differential of these matrices at 0. So dot means a derivative with respect to Z, like this. How it goes. For example, the action of the transfer matrix is something like this, involves X inhomogeneity parameters and also spectral parameter Z. So it's a bit tedious. And you take the derivative at Z equals 0, and then take the alternating sum, and then you recover this formula. So the result is somewhat non-trivial. So at this point, probably it's useful to, I would like to remind you that similar analogous result for the more extensively studied model, which is just ASEP. So ASEP case, it's very simple. So the Hamiltonian consists of nearest neighbor terms, which exchange the local pairs with this transition rate. And this Markov matrix has this well-known origin, sometimes referred to as the Baxter formula. So it's the logarithmic derivative of the sum transfer matrix. But in my notation, this is just a T1, one simplest member of the families of transfer matrix that I introduced. So the K1 case. And also at the homogeneous choice of the parameters. So this result is due to the following property of the basic non-fusion or K equal 1 R matrix at the so-called Hamiltonian point. So the R matrix S11 has a Hamiltonian point. What does it mean? So let's P denote a transposition of the component, then it becomes like this. So that means if Z is 1, then the R matrix like this becomes something like this. So that's the meaning of this formula. And due to this result, which can be easily checked, you can establish this formula. By the way, this logarithmic derivative ordering doesn't matter because they are all commuting. Oops. So the corollary of the two results, the one is the one for the t-PushTASEP, is the second one is this well-known result. The corollary is, so because T1 and Tk is commuting, also at the inhomogeneous specialization, that means H-ASEP and H-PushTASEP with homogeneous choice of parameters is equal to 0. So they are commuting. So they share the eigenstates. So that's a corollary of our result. So actually, because not only T1, but all the Tks are commuting, it is natural to look for the joint eigenvector corresponding to the t-PushTASEP stationary state. So let's introduce this elementary function like this. So this is very elementary, where this Ek is indeed an elementary symmetric polynomial. And I already explained the notation in this case. See? And so using this function, our result is also presented in this manner. So I just, rewritten this constant subtraction using this function. So now, if you look at this formula, it's natural to construct the stationary state of the t-PushTASEP as a joint eigenstate of this form, where this MP denotes a matrix product form like this. So I'm going to construct the stationary state as a joint eigenstate, and also using the matrix product construction. So the most important ingredient in this construction is, of course, this operator A's. So the operators A0 to N are corner transfer matrices, question mark, quotation mark, of a strange five vertex, which is to be explained in detail below. But before doing that, let me just explain the consequence of the so-called homological Fatiev algebra with a structure function S11. So we will establish that this A's satisfy this relation. So here, this factor means matrix element of this guy. So maybe you can interpret this formula as follows. You may given sum, double sum with respect to gamma and delta, but you can take the sum by this formula, ending up with simple factor, scalar factor, and factorize combination product of A and A with X and Z interchange. Yeah, corner transfer matrix. I will tell later. Yeah, I will tell later. So because of the commutativity, the proof essentially leads to the K1 situation. That's enough. So the problem is how to establish this equality for the matrix product constructed states. And pictorially, it's drawn like this. So here, this part denotes a T1, where, for example, L3 side, length 3 chain has been considered. And there is a hanging trace because I'm considering the component equations. So how to establish this relation by using the ZF algebra. So this equation, sharp, well, how to say, natural, is a polynomial equation in Z of degree at most L. So it's sufficient to check at L plus 1 points. So this is a crucial advantage of introducing inhomogeneity. So Z equals 0 is easy, almost trivial. But so let's consider Z equals X1 case. What happens here is this leftmost vertex becomes Hamiltonian point. The spectral parameter becomes 1. So this first vertex becomes like this, as I thought here. So then you can use ZF algebra here for this index. So you have this summation that fit the ZF algebra terms. So then you can push the A with entry X1 to the right, and so on, successfully using ZF algebra relation until you end up with the right-hand side with factorized scalar coefficient. And this is in general not the coefficient eigenvalue is not factorized, as I mentioned. Yeah, this is in general not factorized quantity, but we are considering the Z equal X1 specialization that kills this second factor. It's indeed, the result should be factorized. And you can easily check that this formula is valid. So that's for X1, but there is for some obvious cyclic symmetry of the system. So that's enough to prove all the situation. So that's the end of the proof. Well, almost end of the proof. You need to establish that this trace of the composition is not 0. And
where did you use property of head?
yeah, I applied the ZF algebra at this vertex, and then was very sorry for maybe too small. Yeah, and so this part is kind of fixed, and you can proceed one step further and so on until you get this sort of factorized expression. Okay, is it okay? So I should stress that so ZF algebra is almost enough to establish the stationarity So the only thing that remains is to prove that this trace is not zero and trace is convergent. But that can be done. So this is an example of the stationary state for these sectors, subspaces, and where this cyclic means cyclic permutation. So the coefficients are called ASEP polynomials, although the ASEP stationarity is valid only in the homogeneous specialization. So in that sense, that they may better be called the t-PushTASEP polynomials, but anyway. So from now on, we change the level from local states from this ordering to the reverse ordering, and also reverse take the inverse of Z. So I'm sorry, probably you can guess. I'm switching from one paper convention to another. So before explaining its construction, I mean construction of this corner transfer matrix X or A by a strange 5-vertex model, a brief review of relevant results is in order. Pardon?
In the expression for the stationary measure, there is no normalization constant.
Yeah. So I should say that unnormalized probability. Unnormalized probability. Yeah. Yeah, actually, this normally constant is important. It's going to be McDonald polynomial. So for construction of stationary states of multispecies ASEP on link. So well, I grouped it into the algebraic aspects and the combinatorial results. So for the algebraic, so the matrix product operators was first obtained by these people as a set of very complicated, messy, nested recursion relations. It's very difficult to see what's going on. The later it was kind of simplified by continuity Wheeler, where they showed the background from the representation of the ZR algebra and had the application to the McDonald polynomial. And now from the combinatorial side, so there is a method so-called multi-line Q method. And so T equals 0 goes back to Ferrari-Martin, and the T general case was obtained rather recently Martin and followed by the Williams. So we also had a result for both in both sides. So the T equals 0 Ferrari-Martin algorithm that here can be characterized as most naturally formulated in terms of the quantum groups using the Kashiwara's theory of crystal bases and all. By the way, this morning I found that the Kashiwara got the Abel Prize. And T equals 0, well, this side, the ZF algebra, we got some original proof of ZF algebra by using a tetrahedron equation. That's a 3D analog of the Yang-Baxter equation. So the key in the KMO approach was a 5-vertex model whose Boltzmann weights are taken from T-deformed oscillator algebra at T equals 0. So usually you talk about the Boltzmann weights, it's just number or scalar function. But so this 5-vertex model has got operator valued Boltzmann weights, so to speak. A key for T non-zero ASEP and t-PushTASEP, we get another T oscillator 5-vertex model which obeys a strange weight conservation rule. I was led to introduce such strange situation. So yeah, guided by these works. So it clarifies the relation of the matrix product and multi-line Q methods and refines their derivations. So now here is a strange 5-vertex model. So you consider the vertices 5, there are 5 of them. And my notation is I and J is incoming and A and B are outgoing. And I denote its matrix event like this. And so this is a 2-state model where each H can assume 0 or 1. And the strange weight conservation rule. So usual weight conservation rule is this is vanishing unless the A plus B is equal to I plus J. But now this is replaced by this very strange conservation rule. For example, look at this vertex, very strange, and also this vertex, very strange. And how I had to choose in such manner, I would hope to tell later. It's related to the queuing process interpretation and so on. Now, what is this K and A plus and minus? So they are the generators of the T oscillator algebra whose defining relation is like this. So the natural representation is on a botonic Fock space. And K is a number counting operator, and A plus is creation, and A minus annihilation. So we will also use a number operator H defined by this rule. So the K here is essentially T to the H. So you can regard it as a quantum model or classical model. So in quantum picture, T oscillator weighted to the 5 vertex model. So as I said, you may interpret that the Boltzmann weights attached to each vertex is actually the operator acting on certain Fock space. For example, so I'm show the example of this vertex and this vertex. Sorry, K and A minus. So it acts on certain Fock space vector and get this result and this result. Or you may introduce a third arrow perpendicular to the seat screen or to the vertex and interpret this result as follows. So namely, this newly introduced arrow carries a non-negative integer, which is very different from the other sheet, other direction, just 1, 0, 1. But now this blue arrow carries non-negative integer. And so, but certainly you may regard it as a 3-dimensional vertex model, which is extremely anisotropic in a sense. So from now on, each 2D vertex I should be understood as carrying an arrow, this blue arrow, perpendicular to it, with its own Fock space F running along the arrow on which the copy of the T oscillator act. So if the vertex I, so then I attach an index I to these T oscillators. So now this is the definition of matrix product operator X, originally denoted by A. So this is a pictorial definition. And that's a partial function of the northwest quadrant of the strange 5 vertex model. So that all the edges takes 0 or 1. And you have the summation for the all internal edges and also this bottom edges with a boundary condition that right n edges should be fixed in this manner, according to the index of this operator alpha. And this factor denotes 0 or 1, depending on the edge state is 0 or 1 by this rule. So this can be viewed as a Coulomb transfer matrix of the strange 5 vertex. So I put the quotation mark. Why? So in Baxter's book, he introduced this object as an operator transferring this array of local spins to the vertical array of local spins like this. But in this notation, it is kind of transferring in the perpendicular direction. So yeah, in that sense, but anyway, it's a matter of name. Anyway, so it's a kind of Coulomb transfer matrix. It's a partial function in the triangular region with some boundary condition. So in the classical picture, it is a linear transfer matrix of size n for a 3D vertex model defined on a triangular prism. So this is going to be piled up because you have action of the T oscillators in that direction. So, well, if you are a mathematician, maybe you are intrigued by the following observation. It is a wiring diagram for the longest element of the symmetric group of Sn. So this order is totally reversed. So here is an example of the N2 case. So x0, x1, and x2. So for x0, we choose all these boundary conditions 0, but nevertheless, we have 2 contributions like this. So this bending doesn't do anything. So this is one vertex, and this is another vertex with factor z, because 1 is here. And why this is 1 and a plus, I took it from this definition. So I will have a summation of this factor and this factor, and so on. So this is an example of the N2. And these are the example of the N equals 3. So for example, we have 3 vertices. So that means we have 3 copies of T oscillators, 1, 2, and 3. And actually, that's a layer transfer matrix acting in this blue direction. So it's quite non-local operator. It contains a lot of copies of T oscillators and a lot of summands. Then now our theorem is they satisfy the ZF algebra. So the corollary is the stationary probability of the t-PushTASEP on the periodic lattice is given by this. This is the reason that I already explained before. The DFI algebra is almost enough to assure the stationarity. So I would have to establish that this is non-zero and finite traces convergent, but that can be done. So, but the extra bonus is we have the 3D interpretation because we have natural pictorial representation of these corner transfer matrices. Namely, each corner X kind of layer transfer matrix of the triangular region. So you can, by taking the products, we mean that we pile up these layer transfer matrix in the blue direction and take the trace finally. This is the example for NX3S. Sorry, I missed this part of the. Anyway, so this is a partial function of the 3 vertex model on a triangular prism whose boundary condition is specified according to sigma 1 to sigma L. So that the information about sigmas is specified by these boundary splits. In the bottom, we have free boundary. So after convention, this X alpha reproduced the one in continuity gear paper, where the DFRGL was shown by combining a couple of lemmas. But the diagram representation that I introduced, I mean CTN corner transfer matrix diagram representation based on 5 vertex model is the simplest one devised to date. So it requires only 0-1 states, whereas the one introduced in their papers needs an N color pen for N species models. So next page presents the key ingredients or proof which make use of the corner transfer matrix diagram and elucidate the connection to the quantum group theory. So because we have this diagram representation, you can strip off the rightmost column like this. You can add that the intermediate state is just one place where each state can become 1. And let's label it as I. So then by the construction of figure, we have such regression relations. And we use the induction with respect to n is the number of species. So the important step of the proof is to understand what is this object is. And the factor is linked with the quantum group theory by this formula. So namely, we up to some trivial shift of the indices and well controlled the bottom component of the Q T oscillators, it coincides with some known R matrix, which is expressed like this. So the R matrix is expressed in terms of T oscillators. So the L alpha beta is an R matrix of this quantum algebra or oscillator type representation in this space. So the idea of representing Lie algebra elements as a creation and annihilation operator dates back to Holstein-Primakov. I think spin-raising, lowering operator, they interpreted as a creation and annihilation of bosons to deal with the spin waves. That goes back to this ancient paper. So this is a far-reaching kind of descendant of such idea. But anyway, so in the last 15 minutes, I hope to explain the question. Yeah.
When people construct 2 operators, quantum groups, which is like TQ acceleration, they use also this kind of similar construction.
Sorry.
So quantum group people use the Q operator.
Q operator.
Which is
okay.
TQ relation.
Okay. Yeah, Q operator is not in this story. Yeah.
It's not, there is no relation with the Q operator because to construct them, you also use Q oscillator.
Yeah, certainly there should be a Q operators, Q matrices, but this kind of story is not concerned with that. But maybe, don't know, who knows, it may be coming to the game in future. I don't know. Any other question?
Would that Q be the same Q as the Q in the Donald polynomials?
No, Baxter's Q operator, I think he mentioned. Yeah, capital Q. TQ relation or Baxter relation. Yeah.
Do you think you could put in the Q from the Donald polynomial?
That probably I'm going to explain from now. Yeah. So in the last 15 minutes, I hope to explain the relation to multi-line Q construction. So for simplicity, I only consider the homogeneous case that effectively reduced to the ASEP case. So the appearance of X dependency rather easy or trivial. So I just skip that degree of freedom. So X won't appear anywhere from now on. So what is multi-line Q construction? Actually, what is a multi-line Q? So it's a pair of data. One is a ball table, and one is pairing. Now, what is ball table? It's a diagram like this. So where this side has length L, L is the system size, and depth is N, N is the number of species. And for this square lattice, you inscribe some balls where I draw it at the dot. So it's a ball table or dot pattern. So there are a specified number of balls that you should inscribe. This number is specified according to this rule, where MI is the multiplicity of the color I particle. And so there is an algorithm given this, so that's a ball table. Now what is pairing? Pairing is drawn by this red, blue, and green arrows. So starting from something in the bottom, you try to find a partner and pair them, and so on. So that's a kind of connection. So I'm not going to explain the full detail of this algorithm, but the algorithm tells you that there is an image. Given this information, you can get an ASEP state like this with some coefficient, which is a rational function of Q and T. So the multi-line Q construction due to James Martin and Colte Mandelstam-Williams is a stationary state is obtained as a summation of this image of this map over all possible multi-line Qs and specialized Q to the 1. So the pairing for a given ball table is not unique, and the ASEP states obtained as an image of pi carries a quotient referred to as a weight. So let's look at the example. So here are two same ball table, a dot pattern, and the two same, how to say, connected dots. So the connected dots are the same between Q1 and Q2, but the way to connect them or pair them is different between Q1 and Q2. And so by the rule, the algorithm, so the image is given in this manner. So this is a weight. Actually, this weight let is assigned attached to this connection, and this blue factor is correspond to this pairing, and so on. And yeah. But so this configuration you can see here. So if it's captured by the pairing, it becomes 2. And if not captured, but there is a dot, it's 1. And it's 0 if it's vacant from the beginning. So that's sort of rule. So this weight function, I'm not going to explain it in its full detail, is basically something like this. And so there is some factor which is defined, which can be computed once you know these numbers. And also extra factor where T counts the number of balls that skipped in the pairing. For example, this is a skipped ball here. And also Q counts the number of wrapping of this pairing like this. This sort of, yeah, I'm just trying to convey the flavor of the algorithm. So here, this is the same from the same copy of from the previous page. Now let me introduce the generating function of the weights indexed by A, B, I, J, which are length L, system size, length L, sequence of 0 and 1. So what's the meaning of A, B, I, J? So I is balls downstairs here. So this is 0, 0, 1, 0, 0, 1, 0, 0. J is a ball upstairs. So it's 0, 1, 0, 1, 1, 0, 0, 1, and so on. So A is a connected balls upstairs. So that means 0, 1, 0, 0, 1, like this. And B is unconnected balls upstairs. So this is the generating function of the multi-line Q weights where the dependence A, B, I, J is specified by this rule. So if you know the queuing process theories, so there is some good interpretation. So I denotes the arriving customers. And they can enjoy some service which correspond to J. And so they visit some service counter, which is labeled by A. And there are service desk which is not visited by the customers. That's a B. So that's the interpretation. But if you look at this definition and interpretation, you see that every service is either unused or used. That means A plus B must be equal to D. So maybe this reminds you of some strange weight conservation of the strange five-vertex model. That's the origin. But anyway, so remember that this notation M is for multi-line Q M. So it's a generating function of the weights. Now, let me also introduce another object indexed by same four indices like this. This is a kind of mechanical definition. So we are given these indices A, B, I, J. These are all length L sequence of 0 and 1. So I have I1, I2 through IL and so on. So given that data, I just take this trace. So what is this ABIJ? Let me remind you, because it is so long ago. Sorry. Yeah, here it is. So this is strange five-vertex indices. Yeah, and with some prefactor. So pictorial is like this. So you have product of LS, and each S is the five-vertex weights, but it carries a hidden blue arrow, and you take a composition with respect to that. So Sergei Sergeyev referred to it as a barbecue stick with X-shaped sausages. But anyway, so this S is for strange five-vertex. So remember that we have two objects, M and S, labeled by the same indices. Now, our theorem is, so this M and S is the same, coincide. So let's just observe the examples. So from the previous page, we had two ways to connect these dots. So the Q1 and Q2. So this generating sum consists of two terms. And that's here. On the other hand, for S side, we have size H system. So the A product of S specified by these arrays like this. So that gives you this formula, and it's very pleasant to compute this price using the commutation relation of the t-oscillator algebra. Then you end up with identical result. So namely, the messy sum of the pairing is unified into a single barbecue stick, which is a trace. So what's created or annihilated by the t-oscillator algebra are the customers in the queue. So that's the story about the N equal 2. You just have two rows. But what about the multi-row case? So this is an example of the N3. So you have three rows. The ball table consists of three rows. And you do a lot of pairings and end up with certain configurations in the image and with some complicated rational function as a quotient. So the multi-line Q construction for N greater than 2 is a nested composition of the N equal 2 rule that I explained before in a corner transfer matrix manner as illustrated in the next page. So what do is you start from these bottom dots and try to find a partner in the nearest neighbor rows. And you proceed further and until you reach this point 3 and 3. And then you do similar things starting from the remaining dots in the second row and so on. So let me, for the space reason, turn this multi-line Q diagram 90 degrees and show this aspects, explain these aspects. So now it's 90 degrees rotated. So I start from the column A and try to find a partner in column B or parent B and proceed further to the so on. So I would like to decompose it into two rounds. In the first round, I start from the bottom leftmost column and find the, do the pairing until I reach the rightmost column. So, and remove the connected poles, and I end up with this result. So this part of the procedure, the first round, I would like to draw it in this manner. So namely, I let A penetrate B and C to end up with A prime. So A prime indicates the non-location of the ball of color 3 particles. And thereby you somehow reduced the B and C into B prime and C prime. So that's an effect of the penetration of A, B prime, C prime like this. That's the first round, which concerns a red pairing. The second round, so I do the same thing for the remaining dots, which I denoted by blue arrow. So I start from B prime, C prime, and let B prime penetrate C prime to obtain B double prime. B double prime is these two twos. So each split gives you the position of the color 2 particles. And remaining dots, this one corresponds to this one. But if you look at these two diagrams, you notice that you can put this diagram on top of the first diagram of the first round. That's 2 diagrams combined into a single diagram, which is nothing but the CTM, polar transfer matrix. So that's what I mentioned as a nested composition of the N2 algorithm. And the endpoint result, but in the end, you see that A prime, B prime, double prime, C double prime specify the position of the color, respective colors. So if you want the stationary probability, you need to keep track of the weights for each pairing. So, but that is exactly done by regarding these vertices as M matrix, generating function of weights. So maybe this is a polar transfer matrix consisting of M weights. But we have established that M is equal to S. So you can substitute this vertex as a barbecue stick. So somehow you can dissolve into the layers. So that leads to this diagram is obtained like this. That's the way how we get that result. And during this construction, maybe there was a question about Q. So I skipped that aspect. So for as long as I deal with t-PushTASEP, I have to put Q to the 1 at some point. But this plane holds for generic K, where Q is here, where H is here. Yeah, and yes. So that can be maybe the application to the McDonald polyad may be interesting, but where is Q? I probably mentioned it briefly somewhere. Yeah. So actually, the multi-line Q algorithm, you have to change Q from place to place. That's quite complicated. Yeah. But anyway, so as far as you are concerned with stationary probability, at some point you have to set Q to the 1. But anyway, this theorem holds for NQ. And as I showed in these examples. So let me summarize. So I start from the 5-vertex model. This is not the way I explained, I thought, but maybe we can start from the 5-vertex model, strange 5-vertex model, and form the corner transfer matrix like this. Then with the help of this quantum group theory, you can establish that the DF algebra is satisfied, and that immediately leads that the matrix product formula with 3D interpretation, because each X has got the layer transfer matrix interpretation. So this is the partial function of the 3D classical model. So that's one flow of the story. But on the other hand, you can substitute this barbecue stick formula for the generating function of the multi-line Q to each part of this diagram, namely. So this diagram consists of many such blue arrows. The trace is independently taken from the blue arrows. So then that leads to the multi-line Q construction. So that's another derivation or proof of the multi-line Q construction. Yeah, so I think I'm almost done. So let me finish with PQR. So in the first part of my talk, I introduced our result about the superposition of the transfer matrix with respect to all the fundamental representations. But as you know that fundamental representation has a dimension expressed as a binomial quotient. So that this summation means the effective auxiliary space has this dimension, and which is somewhat suggestive. So maybe, I hope, maybe it's interesting to look for some further simpler reformulation of t-PushTASEP. That's just a speculation. And probably until well, there are many trials to find stochastic models in integrable vertex model, but without much success because the limitation about the probability interpretation is very restrictive. You have to obtain the non-negative weights and summing up to 0 or 1 and so on. And if we look at one particular transfer matrix, that may be too hard, but there may be a chance to do so by combining some suitable linear combinations. So there are further examples of commuting transfer matrices that are not stochastic by itself or individually, but become so through some form of superposition. And maybe to test this idea for type BCD may be interesting. This is another speculation. And the proof of the GF algebra, we relied on the induction with respect to n, which I do not like, actually. So, and actually, when t was 0, we could prove it directly by using the tetrahedron equations. And it's still an open problem to find such a proof. So I stop here. Thank you.
Questions? I have another question. So again, about the normalization constant for Q equal, so the normalization constant of the stationary states should be the Magnum polynomials at Q equal 1. So it means that there is some representation in terms of barbecue stick or matrix product form for these Magnum polynomials.
By what you said?
Using your matrix product form or your barbecue sticks, you can express Magnum polynomials at Q equal 1.
Yes, I think even Q equal general.
And general Q also.
Yeah. So, well, yeah. So, where is? Yeah. So the Magnum polynomial should be the summation of the trace of many product A's, and including Q. Yeah.
And this works for any Q.
Yeah. Where is it? Yeah.
I have another question. You were mentioning some inclusion-exclusion rule at the very beginning of your talk. So do you think that there should be a probabilistic interpretation of the formula that you showed, the sum of a k of -1 to the k, and then the 5 vertex transfer matrices?
Yeah, I hope to find such interpretation, but at the moment, I don't know. Yeah. Yeah, maybe the last comment is you can, sorry. Yeah, I expressed that t-PushTASEP Hamiltonian in this as an alternating sum involving the signs and also the derivative. But you can try to express this same t-PushTASEP Hamiltonian using the transfer matrix for symmetric fusion. That's a lower index tk. So that's the reason I use a superscript to denote anti-symmetric fusion. So if you use a lower index symmetric fusion, which is very common in the literature, then you end up sort of kind of messy formula. And so first we got this and didn't know how to do with that. Yeah, and then we switched the anti-symmetric fusion, and it worked very neatly. And but I'm not sure if this sort of formula helps. Yeah.
Further questions? Otherwise, we can thank Professor Kuniba again.